Section: Introduction. In this section, we explore the impact of training language models on the search process. We aim to teach language models how to search and backtrack, allowing them to self-improve. Transformer-based models have struggled with planning tasks, facing issues like error compounding and look-ahead challenges. These problems stem from the model's limited ability to search and backtrack effectively. While some approaches have combined language models with symbolic search algorithms to address these issues, they only assist during inference, leaving unanswered whether language models can conduct search independently. Learning to search during training could greatly benefit language models. By mastering search techniques early on, models may develop more adaptable strategies to handle error compounding and look-ahead tasks. We demonstrate that language models can be trained to search and backtrack by representing the process as a stream of search, SoS. We define components like exploration, backtracking, and pruning in a unified language and apply them to a search problem inspired by the game of Countdown. Countdown presents a challenging search problem where input numbers must be combined with arithmetic operations to reach a target number. We create a training dataset of search trajectories using symbolic planners and heuristic functions, training a language model on this diverse dataset. Comparing this approach to training solely on optimal solutions reveals that the stream of search LM outperforms models focused on predicting optimal steps. Furthermore, when fine-tuned for correctness using advantage-induced policy alignment and expert iteration, the stream of search model shows enhanced search and planning abilities. Our results suggest that transformer-based language models can learn problem-solving through search and improve their search strategies autonomously. Training for accuracy also leads to the discovery of new search strategies. In related works, previous methods integrated language models into search systems to generate actions and evaluate states. However, these methods primarily focus on inference, lacking improvement in reasoning abilities. In contrast, our approach trains language models to explore, backtrack, and reason effectively, learning an intrinsic policy for autonomous search. This eliminates the high inference costs associated with fixed search strategies. Other approaches, like in-context demonstrations of search and process supervision, have limitations in terms of demonstrated search procedures and scalability. Our method directly enhances the model's planning and search capabilities without the need for a verifier reward model. While similar works train transformer models on search trajectories, our emphasis lies on autonomous search procedure usage and the discovery of new strategies, distinguishing our approach from existing methods. Section Summary. In this section, we explore the impact of training language models, LMs, to learn from mistakes and search processes, allowing them to self-improve. By teaching LMs to search and backtrack during training, they can develop more flexible search strategies, enhancing their problem-solving abilities. Our study demonstrates that transformer-based LMs, when trained to recover from errors and explore different options, can autonomously employ various search strategies, leading to solving previously unsolved problems and discovering new search approaches. Section: A language for search. In this section, we model the problem space as a Markov decision process, MDP. The MDP consists of states representing problem-solving steps, actions that can be taken, a transition function defining state changes based on actions, and a reward function for reaching the goal state. The search process starts with an initial state and aims to reach a goal state by exploring a search tree. This tree includes all possible actions from the initial state to its child states until a solution is found. A correct path to the solution is a sequence of states and actions leading from the initial state to the goal state. We focus on the search process within the search tree. To represent this process, we introduce primitive operations like the current state being explored, the goal state, a queue of states to be explored, an expansion function to explore adjacent states, and choices for exploration order. Other operations include pruning, backtracking, goal checking, and using heuristics to estimate distances to the goal. These operations can be implicit or explicit in the search trajectory. We choose to make the current state, goal state, backtracking, goal checks, and exploration choices explicit in the trajectory. However, we keep heuristic functions, state values, and pruning strategies implicit. For our task example, Countdown, a variation of the 24 game, we demonstrate the use of search streams. Countdown involves combining input numbers with arithmetic operations to reach a target number. We select this task due to its complexity, requiring planning, search, and backtracking for solutions. We focus on problems with 4 input numbers and target numbers ranging from 10 to 100, with 10% of targets held out for evaluation. Section Summary. In this section, we model the problem space as a Markov decision process, MDP, with states, actions, transition functions, and reward functions to represent the search process. We define a search tree starting from an initial state to a goal state, where a correct path to the solution is a sequence of states and actions. We introduce a vocabulary of primitive operations like state expansion, exploration choice, pruning, backtracking, goal checks, and heuristics to guide the search process efficiently. Section: Training Data. In this section, we trained a model on streams of search for Countdown by creating a synthetic dataset with diverse and suboptimal symbolic search strategies. We defined 12 search strategies based on breadth-first search, BFS, and depth-first search, DFS, using simple heuristic functions. These heuristics guide the search based on the absolute difference between remaining options and the target sum, and the distance to the factors of the target. Our dataset consisted of 500,000 search trajectories, with only 57% leading to the solution. Each search trajectory is represented as a string of tree nodes, states in traversal order. We evaluated the model's accuracy in generating correct solution trajectories for Countdown problems. We measured correctness by checking if the correct path to the solution was present in the generated trajectory. We also analyzed the alignment between different search strategies based on the problems they solved correctly and the states they visited. We then compared training models on clean, optimal solutions versus messy and sometimes unsuccessful search trajectories. Training on search trajectories outperformed training on optimal solutions, achieving 51.27% accuracy on held-out inputs compared to 25.73%. Despite having fewer training examples, the model trained on search trajectories performed better. It faced a more challenging task than symbolic search methods but still generated valid trajectories with low error rates. The trained model showed alignment with various symbolic strategies, with the highest correlation observed with DFS using the sum heuristic. The model did not rely heavily on any single strategy from its training data. Section Summary. In this section, we construct a synthetic dataset for training a model on streams of search for Countdown by defining 12 search strategies based on BFS and DFS with interpretable heuristic functions. We compare models trained on optimal solutions versus suboptimal search trajectories and find that the model trained on streams of search outperforms the one trained on optimal solutions, achieving higher accuracy on held-out inputs and targets. Despite facing challenges, the model trained on suboptimal search trajectories demonstrates effective learning and alignment with various search strategies, showcasing its ability to generate valid trajectories with low error rates. Section: Policy Improvement with Stream of Search. In this section, we aim to investigate if our model, the Stream of Search Language Model, SoS-LM, can enhance its problem-solving capabilities beyond what it has learned from its training data. We want to see if the model can improve itself based on feedback regarding correctness and efficiency. To assess this, we test the model's ability to solve problems that were previously unsolvable using the symbolic search strategies it was trained on. We also challenge it with difficult problems from the training set that none of the symbolic search strategies can handle. To enhance the model, we employ 2 reinforcement learning (RL) strategies. Expert iteration using STAR and advantage-induced policy alignment, APA. With STAR, we fine-tune the model by generating correct trajectories from the training dataset and using them to update the model iteratively until we observe improved performance on the validation set. On the other hand, APA involves creating a copy of the language model to serve as a value network, which is then used to enhance the original model's policy. We design a reward function based on correctness and trajectory length to guide the model's learning process. Our experiments show that after 3 iterations of star fine-tuning, the SoS models exhibit improved performance, solving additional problems beyond the base model. Similarly, when fine-tuned with APA, the models show enhanced accuracy, although the validation accuracy stabilizes after a certain number of training steps. By analyzing the state visitation patterns, we observe that both STAR and APA models explore more states associated with specific heuristics, indicating their ability to employ diverse search strategies. Furthermore, the SoS models, enhanced with STAR and APA, demonstrate better error handling and faster solution finding compared to the base model. These improvements suggest that the models can effectively utilize various search strategies, potentially discovering new heuristics and search methods. Our results highlight the effectiveness of training language models to search for solutions, emphasizing the importance of exposing models to the problem-solving process rather than just optimal solutions. Overall, the SoS framework shows promise in enabling language models to tackle complex problems through internal search mechanisms. By incorporating feedback mechanisms like STAR and APA, we can guide the models towards self-improvement and enhance their problem-solving capabilities. Section Summary. In this section, we explore if the SoS LM can enhance its symbolic strategies through self-improvement based on correctness and efficiency feedback. By utilizing RL strategies like STAR and APA, we observe significant improvements in solving previously unsolved and difficult problems beyond symbolic search strategies. The SoS models show enhanced performance after iterations of fine-tuning with STAR and APA, demonstrating the ability to flexibly utilize various search strategies and discover novel heuristics. Section: Acknowledgements. In this section, we express our gratitude to Gabriel Poesia, Jacob Andreas, Joy Hee Yuya, Dongwei Zhang, Eric Zelikman, Jan Philip Franken, and Si Zhang for their valuable discussions and support. Our research was made possible thanks to the funding from the Stanford Human-Centered Artificial Intelligence (HI) Google Grant and the NSF Expeditions Grant with award number 1,918,771.